Welcome to this explainer. I want you to picture something absolutely wild. Just imagine a skilled shipyard worker holding a gas torch, moving it in this really slow, straight line across a massive, perfectly flat steel plate. At first glance, absolutely nothing seems to happen. But then, as you step back, you realize the impossible is basically taking place right before your eyes. That solid, incredibly heavy steel plate is now clearly curved. And not just in one direction, but in two. And honestly, the craziest part of all this, there was literally zero mechanical force applied. No giant presses, no heavy rollers, just a worker, a torch, some water, and a seriously profound understanding of metallurgy. This is heat line bending, and it is undoubtedly one of the most highly skilled and almost magical crafts in modern shipbuilding.
Okay, let's dive into this, because it states the core mystery right up front. How exactly can fire bend steel without a press? You know, when we think of shaping industrial steel for something as massive as a modern cargo ship, we naturally picture heavy mechanical force, right? Massive hydraulic machines exerting just thousands of tons of pressure. But heat line bending entirely defies those expectations. We are completely replacing brute force with applied thermal physics. Now, to understand exactly why we do this, we first need to look at the structural problem we're actually trying to solve.
And that problem is double curvature. So what is that? Well, double curvature is a surface that's curved in two directions simultaneously. Think of the shape of a horse's saddle or, the complex sweeping hydrodynamic curve of a ship's bow. Now, shipyards have these massive hydraulic plate rolls, and sure, those are great for bending steel, but they can really only produce a single curve, kind of like a section of a simple cylinder. If you need a heavy plate to bend in two directions at once to get that perfect hydrodynamic hull shape, those standard rolls just simply cannot do it. The machinery literally falls short. So we have to turn to fire.
All right, moving into Section 1, the physics of heat forming, from macroscopic magic to molecular science. Now, as much as it looks like it, this isn't magic. It's a deeply controllable physical process. The whole secret lies in this phenomenon called plastic compression. And I really want you to focus on this concept for a second because it is entirely counterintuitive. We usually think that when you heat metal, it expands, right? And well, that's true. But in this specific technique, heating a really small, localized zone of steel actually causes it to permanently shrink once it cools down. It's almost like a muscle contracting. And it's this physical shortening of the steel that literally pulls the massive plate into a curve. But you're probably wondering, how on earth does heating cause shrinking? Let's walk through the molecular physics step by step here, because it is just fascinating. Step 1. The worker applies the torch to heat a localized zone on the top surface of the plate. Those heated molecules get energized and they desperately want to expand. But here comes step 2. That hot zone is entirely surrounded by a massive area of cool, rigid steel. That cool metal essentially acts like a vice. It absolutely constrains the expansion. So, step 3. Because the hot steel is forced to expand against the unbreakable constraint of the cool steel around it, it actually undergoes plastic compression. It literally squishes into itself, physically shortening its own structure. And finally, step 4. When the torch moves away and that specific zone cools down, it contracts to its new, shorter length. Because the top surface is now permanently shorter than the bottom surface, the entire heavy steel plate curves toward the side that was heated. Boom, thermal stress forming.
Which takes us to Section 2, drawing shapes with heat, the art of thermal patterning.
So once you grasp that controllable thermal stress is what bends the plate, the next question is, how do you get the exact shape you need for a ship's hull? And this brilliantly illustrates how the specific pattern of heat directly dictates the final geometry. If a worker draws straight, parallel heat lines across the plate, the result is a cylindrical single curve. If they draw radiating fan lines, starting from a single point and spreading out, the plate will actually warp into a cone-like compound curve. And if they apply heat in triangular patches, they create these localized bowl-shaped curves. So by combining all these patterns, a worker can basically force the flat steel to take on incredibly complex, mathematically precise forms. But here is where the true awe of the craft really comes in: mental 3D translation. An operator has to look at a highly complex 3D target geometry, which is usually derived from a digital CAD model of the ship, and then mentally translate that finished 3D shape into a flat 2D pattern of heating lines. They have to know exactly where to apply the torch, in exactly what pattern, and in what specific sequence to make that flat steel organically rise up into the exact shape required.
I mean, this is a level of craftsmanship that takes years, sometimes literally decades, to truly master.
Section 3. Locking curvature with water. The technique.
So applying the heat is really only half the battle. We also have to lock that curvature in. And the crucial element here is rapid water quenching. If you've ever watched this process on a shipyard floor, you'll see a second worker, or sometimes an attached nozzle, following immediately behind the gas torch with a water hose. The water instantly quenches the heated zone, sending up these huge plumes of steam. This rapid cooling essentially freezes or locks the plastic deformation in place before the elastic nature of the steel can cause it to just spring back. But get this, it's not just about locking the shape. The water actually controls the shape too. The rate of the quench dictates the amount of shrinkage. A faster quench means more contraction, which equals a tighter curve. So the exact timing and distance between the intense heat of the torch and the cooling shock of the water relies incredibly heavily on the operator's intuition. They are literally constantly balancing fire and water to sculpt solid steel. Moving into Section 4, From Craftsmen to Robots, the Evolution of Heatline Bending.
As modern yards look for more consistency, we're seeing this fascinating direct comparison between human intuition and machine precision. Now, what's really interesting about this slide is how clearly it contrasts the two. On the left, we have our traditional human operator. They're relying entirely on their mental 3D translation, manually pacing the torch in the water, and leaning on decades of acquired craftsmanship. Then, on the right side, we see what modern yards are introducing: semi-automated robots. These robotic arms follow super precise paths directly programmed from the 3D CAD geometry. They control the heat input perfectly, and they use real-time sensors to actually measure the developing curvature of the plate after every single pass, automatically adjusting the next one to hit the target shape. It's a huge shift that drastically reduces the dependency on that rare, highly specialized skill of human operators.
However, don't write off the humans just yet. The machines haven't taken over completely. Fully complex bow sections, which are the most extreme, hydrodynamically complicated curves on the entire vessel, still very often require experienced human operators for those critical final passes. The robots can definitely get the plate about 90% of the way there, but those nuanced, intuitive adjustments required to perfect a massive double curvature plate, that still fundamentally demands the human eye and the human hand.
It all perfectly summarizes our journey today. As the quote says, shaping steel with fire is truly one of the most counterintuitive techniques in manufacturing. I mean, we started with what basically looked like an unbelievable visual illusion on a flat steel plate, and we've broken it down to see the masterfully applied metallurgical science underneath. It really is this perfect balancing act of thermal expansion, constrained plastic compression, and rapid water quenching, all working together to sculpt the skin of the absolute largest moving structures on Earth.
Which leaves us with a pretty fascinating final thought to ponder. If our absolute oldest tool as a species, fire, is still fundamentally required to shape the most modern, technologically advanced megaships sailing the oceans today, well, what other ancient elements and traditional crafts are hiding just beneath the surface of our futuristic factories? The plates are formed. Now the frame members, the skeleton of the ship, also need bending. Thank you so much for joining me for this explainer. I really hope it sparked your curiosity to look just a little bit closer at the industrial marvels all around us.